Hi everyone, it's Miss Thomas, and we are going to look at linear functions versus exponential functions in this video. So for linear equations, there's a common difference for the x and y, whereas for exponential equations, there's a common ratio for the y values instead of a common difference. So what does that look like? For my linear function, I might have 0, 1, 2, and it might start at 5, go to 10, and then go to 15. So my common difference is that for each change in 1, for the x, I am increasing by 5 in the y. Whereas for exponential, I might start at 5, go to 10, but then I would go to 20. Because for exponential, for each increase of 1 for the x, I'm actually doubling it for the y. So it's not always doubling, but it's some common ratio that you're using. So I could figure out what my next term would be by following the pattern in each respective table. So it'd be 20 there, whereas this would be 40 for the third term. So you can see that linear increases at a steady rate exponential increases rapidly, or it decreases rapidly if it's a decay problem. So the equations for each of these is a little bit different. So for linear, we can have slope-intercept form. We've got several forms, right? But most frequently seen is y equals mx plus b, where m is your slope, and b is your y-intercept. And if you recall, when we think about these equations, your slope is your common difference. And your y-intercept is your starting amount. So if we looked at the tables that we've got, my equation would be y equals, and then from the table, 5, x will stay in x, and then from the table again, your starting amount is, and your y-intercept is where your x equals 0, so it would be 5 again. So the linear equation for the relationship would be y equals 5x plus 5. Whereas for the exponential function, the equation is y equals ab to the x. When you don't have anything add or subtract on the end, this is your starting amount. And the b is your common ratio, or your rate. So in this equation, we would have y equals, our starting amount for this one is also a 5. Our b, our rate, is this times 2. That is an ugly looking equation with those colors, but y equals 5 times 2 to the x would be the equation that models the exponential growth. So here we have just a few examples with tables. So in example 3, which of the following functions would best describe the data in the table. So we've got these 4 examples. What we want to do before we jump into the equations is try to look to see what the pattern is in the table. So my x's are increasing by 1, and my y's, they could either be increasing by 8 or times 5. Those are the 2 ways you can get from 2 to 10. So you need to look at the next one to see that the pattern must be times 5, because 10 to get to 50 is going to be a multiple of 5. So since it is multiplication and not addition, it has to be exponential. This is linear. This is linear. I know it's linear because it doesn't have an exponent. That's a variable. Whereas these are exponential because those variables are in the exponent. So we know it has to be either 3 or 4, and we want to think about what we just talked about, where y equals ab to the x. A is our initial amount, and b is our rate. Remember, your rate is how you get around, so our rate has to be 5. So this one has a rate of 5. 5 is being raised to the exponent. It also has that initial amount of 2, so we know the answer has to be 4. So if you're asked to find the equation of the exponential equation, y equals ab to the x, again, they're already telling you it's exponential, so you know that for every increase in your x, you should be multiplying by something in your y. So 10 to get to 30 is going to be times 3, 30 to get to 90 times 3, 90 to get to 270 times 3. So this is my rate, my initial amount. So y equals 10 times my rate to the x. Example number 5. Write an equation of the function represented in the table. So to get from -1 to 0, we would add 1, so we're adding 1 every time for my x's. 2/3 to get to 2. I know a lot of you would probably struggle with that. The only difference between these is that denominator of 3 is gone. So to get rid of a denominator of 3, you'd have to multiply by 3. And we can see that that holds true because 2 times 3 is 6, 6 times 3 is 18, and so on. So this is exponential. And its equation, I'm going to sneak in down here, ab to the x. So my b is my rate is the times 3. My a is my starting amount. My starting amount is where my x is equal to 0. So it's 2. So one last example, we want to write an equation of the function represented in the table. So for every change in 1, I am subtracting, not adding, a 0.5, 1/2. Minus 0.5, minus 0.5. So, because it's addition or subtraction, it's a linear equation. So then you want to use y equals mx plus b. This is your rate, and this is your starting amount. Well, my rate is still the change in the y's. It's a negative 0.5. X stays an x, and then I need to look for my b, which is where my x is equal to 0. And it's what my y value is there.